The entire system, which stores, carries and controls the fuel supply for the engines, can be divided into two sections: the airframe fuel system and the engine fuel system. Here we'll look specifically at the engine fuel system, which receives the low-pressure fuel supply from the aircraft fuel tanks, which are part of the airframe fuel system. The engine fuel system increases the fuel pressure to a value that the fuel nozzles in the combustion chamber can use, and then controls the volume of fuel into the engine so that it conforms to the engine's requirements. The engine fuel system consists of a number of components which we'll now describe in more detail. The booster pumps, which are situated in the wing and centre tanks of the airframe fuel system, pass fuel through non-return valves to the engine via the low-pressure fuel cock. The low-pressure fuel cock is electrically operated. It can be shut automatically if the engine fire control handle is activated. If a component of the fuel system needs to be removed, for whatever purposes, the low-pressure fuel cock can be used to shut off the supply of fuel to the engine to facilitate the removal. If the high-pressure fuel cock cannot be used to shut down the engine for whatever reason, as an alternative, the low-pressure fuel cock can be used to stop the engine. However, using the low-pressure fuel cock to shut down the engine instead of the high-pressure fuel cock will mean that the engine will take much longer to shut down. This is because the pipeline between the low-pressure fuel cock and the engine contains a considerable amount of fuel, which will maintain the supply to the burners for some time, whereas in the case of the high-pressure fuel cock, very little fuel is contained in the pipeline between it and the combustion chambers. After it's passed through the low-pressure fuel cock, the fuel then enters the engine fuel system and is delivered to the low-pressure fuel pump. The low-pressure fuel pump is sometimes called the backing pump because it will attempt to back up the fuel supply to the engine in the event of failure of both of the booster pumps in the wing tanks. The low-pressure fuel pump is used to supply positive fuel pressure directly to the high-pressure pump. By maintaining a positive pressure, the low-pressure pump minimizes the chance of cavitation occurring at the inlet of the high-pressure pump. The low-pressure fuel pump is driven by the engine's accessory gearbox, which itself is driven by the high-pressure compressor shaft. A fuel-cooled oil cooler is fitted in the majority of gas turbine engine installations. The oil cooler serves the double purpose of cooling the oil and also heating the fuel. By raising the temperature of the fuel, the oil cooler eliminates the formation of ice crystals, which may block components downstream in the fuel system. The oil feed line to the fuel-cooled oil cooler incorporates a pressure-maintaining valve. This valve keeps the oil pressure in the cooler higher than the fuel pressure. If the oil cooler does develop an internal leak, then the fact that the oil pressure is higher than the fuel pressure will ensure that the oil leaks into the fuel system, rather than the fuel leaking into the oil system, which could be very dangerous. The fuel heater assists in the warming of the fuel, and thus the elimination of ice crystals. The fuel heater, working in conjunction with the fuel-cooled oil cooler, uses compressed bleed air to warm the fuel to automatically maintain a predetermined fuel temperature. The automatic temperature control can be achieved by the action of a Vernotherm thermal actuator. The thermal actuator incorporates a material which is sensitive to temperature change. This is used to open or close a valve which regulates the entry of hot air into the fuel heater from the engine compressor. The low-pressure fuel filter is the first line of defense, protecting the delicate control components within the high-pressure fuel pump and the fuel control unit from the effects of dirt or contamination. The low-pressure filter is usually a replaceable paper filter element, which is capable of filtering out particles larger than 50 to 100 microns. The flow meter measures the instantaneous fuel flow in gallons per hour, kilograms per hour, or pounds per hour. The flow meter may also include an integrating system, which can add the total amount of fuel used. There are basically two types of flow meter in use on large jet aircraft. They are the vane type and the mass flow measuring type. The vane type of fuel flow meter, which is fitted to older aircraft systems, is designed to measure volume of flow. The flow meter consists of a vane which is moved against the force of a restraining spring by the volume of fuel flowing past it. This system is not too accurate. The mass flow type of instrument can be accurate to within plus or minus 1%. Fuel flowing through the instrument rotates both a drum and a spring-mounted impeller, which have magnets fixed to them. Movement of the magnets is sensed by pickup coils, which translate the difference in angular displacement between the magnets into a mass flow rate. The fuel temperature is sensed as the fuel leaves the fuel heater. Fuel temperature is indicated on the flight deck to allow system monitoring. The fuel pressure is sensed as the fuel leaves the low-pressure fuel filter. Fuel low pressure may be indicated by either an LP fuel warning light or the activation of warnings on the ICAS or ECAM, depending on aircraft type. The high-pressure fuel pump is fitted to and driven by the engine accessory gearbox. The engine accessory gearbox itself is driven by the high-pressure compressor shaft. The high-pressure fuel pump illustrated is representative of one type of pump employed. It's a plunger-type pump. It can be used as a single unit if the volume of fuel required is not too great, but in larger engines 2 units can be driven together to supply a greater fuel flow. Several plungers are fitted on a rotor assembly. The plungers are rotated against a stationary cam plate, which causes them to reciprocate within the bores that contain them on the rotor assembly. The distance that the plungers move during this reciprocating action is dictated by the angle of inclination of the cam plate. Here we see the cam plate angled so that the plungers stay in the same position in their bores as the rotor drives them round. Now the cam plate angle is such that the springs force the plungers to their maximum stroke when they are at the top of the cam plate, sucking fuel into the bores. And the cam plate forces the plungers to their minimum stroke when they are at the bottom of the cam plate, forcing fuel under pressure to the outlet of the pump. The angle of inclination of the cam plate is controlled by a servo piston, which itself is controlled from the fuel control unit. Most fuel systems incorporate a fuel filter into the output of the high-pressure fuel pump to prevent very fine particles entering the extremely small passageways inside the fuel control unit. The fuel filter is composed of a number of wire mesh screen discs. The spur gear type fuel pump is simpler and lighter in construction than the plunger type fuel pump, and like the plunger type pump, the spur gear type pump is driven by the accessory gearbox. The output of the spur gear type pump is directly proportional to its rotational speed. The fuel control unit controls the fuel flow to the burners for every thrust setting. There are 2 types of hydromechanical fuel control systems still used on gas turbine engines. They are the pressure control system and the proportional flow control system. The proportional flow control system is the more popular of the 2 types because it is more compact than the pressure control system, and it's not sensitive to the effective flow variations that occur downstream of the throttle. The proportional flow control system is the type we'll use to describe the individual parts of a fuel control unit. Various devices within the fuel control unit are used to adjust the fuel flow to cater for variations in air intake pressure, engine acceleration control, exhaust gas temperature, RPM limiting, and compressor delivery pressure. Variations in air intake, or P1 pressure, require that the fuel flow to the burners is adjusted so that a fixed RPM is maintained for a selected throttle position at all altitudes and airspeeds. This is achieved by the expansion or contraction of a capsule influenced by P1 pressure, which in turn modifies the fuel flow to suit the new conditions. This capsule, known as the barometric pressure capsule, is incorporated in an altitude sensing unit within the fuel control unit. It's necessary to increase the fuel flow to the engine to make it accelerate. However, too rapid an increase of fuel flow into the engine can cause compressor stall and surge. To regulate the fuel flow under conditions of engine acceleration, an acceleration control unit is fitted within the fuel control unit. The acceleration control unit receives information regarding engine intake pressure, P1, and compressor delivery pressure, P3 for a two-spool engine, and uses this information to adjust a fuel metering plunger. The fuel metering plunger effectively acts as a second throttle valve in series with the main throttle, and it regulates the fuel flow to achieve the fastest engine acceleration without causing stall or surge. Exhaust gas temperature is probably the most important parameter in a gas turbine engine. To obtain maximum efficiency, the engine must be run at the highest possible temperature in the turbine without melting the materials from which it's made. To achieve these conditions and yet still allow the engine to be a practical, user-friendly unit, automatic monitoring of the exhaust gas temperature is combined with a top temperature control unit. The top temperature control facility allows the pilot to select full power at any time without risking a meltdown in the turbine assembly. Thermocouple probes are positioned in the gas stream, either within the turbine assembly or close after it. The output of these thermocouples is used to measure the temperature at the rear of the engine. This output is passed both to the cockpit instrumentation and to a temperature control signal amplifier. The electrical output of this amplifier drives the solenoid, which indirectly controls the fuel flow to the engine. The ability of the compressor to withstand internal pressure is limited by the strength of the materials from which its casing is made. If the compressor casing is subjected to pressures greater than its design maximum, it will break, with probably catastrophic consequences. To prevent compressor casing failure, the fuel control unit incorporates a power limiter device. The power limiter receives signals of both intake pressure, P1, and compressor delivery pressure, P3. The ratio of P3 pressure to P1 pressure can be found by combining these signals. A system of capsules and levers controls the fuel flow to the engine so that a maximum pressure ratio is never exceeded, and thus the integrity of the compressor casing is retained. If excessive centrifugal force is to be prevented from destroying the compressor spools, their maximum rotational speeds must be limited. There are basically two methods of achieving this compressor rotational speed limitation. The first method of controlling the rotational speed of a compressor, usually the low-pressure compressor, depends on an electrical signal proportional to the speed of the compressor shaft. A tachogenerator or electronic speed sensor, which is driven by the appropriate shaft, sends signals to an amplifier. If the output of the tachogenerator approaches a predetermined maximum level, the fuel flow will be adjusted to prevent the maximum RPM being exceeded. The second method of controlling the rotational speed of a compressor is normally used to control the speed of rotation of the high-pressure compressor shaft. This high-pressure compressor shaft drives the accessory gearbox, which in turn drives, among other things, the high-pressure fuel pumps. Fitted within the high-pressure fuel pump is a hydromechanical governor. The hydromechanical governor uses hydraulic pressure as its controlling parameter. The hydraulic pressure, which is generated inside the pump by the rotation of the moving parts, is proportional to engine speed. As engine speed, and thus hydraulic pressure, builds, it acts on a diaphragm. Movement of the diaphragm opens valves which bleed off some of the servo piston pressure, which reduces the high-pressure fuel pump cam plate angle. This reduces the high-pressure fuel pump output and attenuates the fuel flow to the burners. The high-pressure fuel cock, sometimes called the high-pressure fuel shutoff valve, controls the flow of fuel between the fuel control unit and the fuel spray nozzles in the combustion chambers. The high-pressure fuel cock is the control normally used for starting or stopping the fuel supply to the engine. The high-pressure fuel supply may be mechanically controlled by a lever on the flight deck, or it can be electrically controlled by an actuator, which is also controlled by a switch on the flight deck. When the engine is shut down, any fuel remaining in the fuel manifold would tend to boil as a result of residual engine heat. Solid deposits resulting from the boiling will clog the fuel lines into the system, which would be detrimental to the operation of the engine. The dual inlet line fuel spray nozzle system can utilize a pressurizing and dump valve to prevent this happening. When the engine is shut down, fuel pressure generated by the opening of the high-pressure fuel cock, which was holding the dump valve closed, is lost. The spring inside the dump valve will now be able to open the valve and allow the contents of the fuel manifold to pass back to the supply line. At the same time, the inlet check valve will close, maintaining fuel inside the unit ready for the next start. When the high-pressure fuel cock is opened, a signal of fuel pressure is sent to the dump valve, which moves over and shuts off the fuel flow back to the supply line. In moving over, the valve also opens the passageway to the primary manifold. Fuel pressure from the fuel control unit will open the inlet check valve and pass through the filter to the primary fuel manifold. At a predetermined engine speed, the fuel pressure from the fuel control unit will build sufficiently to open the pressurizing valve, and fuel will also begin to flow into the main manifold, expanding the fuel spray pattern and assisting in better atomization. Many modern gas turbine engine installations utilize electronic engine control to enable better fuel economy, better reliability, and prolonged engine life. Two types of electronic engine control are currently in use: the supervisory engine control system, the full authority digital engine control system. The supervisory engine control system uses a computer which receives inputs of various engine operating parameters and controls a standard hydromechanical fuel control unit. The fuel control unit responds to the electronic engine control commands and performs the functions necessary for engine operation and protection. The computer will monitor EPA, throttle lever angle, Mach number, engine intake pressure and temperature, and will maintain a constant thrust regardless of changes in air pressure, temperature or flight environment. Any fault with the electronic engine control will cause the system to revert to manual control. The Full Authority Digital Engine Control System, commonly called by its initial letters FADEC, receives all the necessary data for engine operation and takes over virtually all of the steady-state and transient control functions, which includes compressor airflow control. The hydromechanical fuel control unit is now redundant, except for the throttle valve and fuel shutoff cock, which reduces the mechanical complexity of the engine fuel system. The FADEC system will monitor all of the normal engine parameters and prevent limitations being exceeded while controlling the engine through all modes of operation, for example starting, idle, acceleration and deceleration, takeoff, climb and cruise. In other words, it controls the engine in response to the throttle lever position or the flight management computer thrust demand. The digital computer which is required to run the system has to be considered an essential component of the engine, just as essential as the compressor or the turbine. This is because a complete failure of the FADEC system would cause the complete loss of the engine thrust. To minimize the chances of a single failure causing the loss of an engine, the FADEC system incorporates two separate identical digital channels. Each channel is able to provide information to enable all engine functions. The FADEC system can be powered from the aircraft electrical system, but in most modern aircraft the system is driven by a separate generator fitted to the accessory gearbox of the related engine. This concludes